You ever stop and think about how your email just knows what's junk? Or how a computer can spot something on a medical scan that a human eye might miss? It really feels like magic, but it's not. It all comes down to one simple idea: sorting. And today, we're going to pry open that black box and look at the two main ways machines actually learn to tell one thing from another. Just think about it for a second. Spam filters, medical imaging, the credit score that could decide if you get a loan. We put a whole lot of trust in these systems every single day. So what is the one thing that connects all of them? Well, at their heart, they're all just incredibly good sorters. They take in this massive flood of information, and their main job is to do one thing: classify it. They're basically just putting data into different buckets: spam or not spam, healthy or not, high risk or low risk. But that's the real mystery, isn't it? How does a pile of code learn the rules to sort stuff so well? Turns out there's not just one answer. Machines have different, well, let's call them thinking styles. So let's dive in and take a look at two of the most popular and powerful ways they do it. Okay, so first things first, let's really nail down the basic problem we're asking the machine to solve here. It's all about this idea of classification. So imagine you've got a chart, and it's covered in two different kinds of dots. Let's say one kind represents benign cancer cells and the other malignant ones. The whole goal, the entire game, is to draw a line, what we call a decision boundary, that gives you the absolute best separation between those two groups. Once you have that line, the machine can look at any new dot and know instantly which side it belongs on. And that leads us right into our first method. This one thinks like a master geometer. Its only goal is to find that single, perfect, ultimate dividing line. And this is the logic behind something called a support vector machine. A support vector machine, or SVM for short, is honestly one of the most successful machine learning algorithms out there. Its whole philosophy is built around finding an optimal separating hyperplane. Now, I know that sounds super technical and complicated, but all it really means is the best possible dividing line, the one that splits your data with the most confidence. So how does it pull this off? Well, you can think of it as a three-step process. First, it just looks at all the data points. Second, it finds the line that separates the two groups. But here's the magic, the really crucial third step. It doesn't just find any line. It finds the line that creates the widest possible street, or margin, between the two groups. The wider that margin, the more confident the classifier is. And this is the really cool part, and it's where the name comes from. You see those data points sitting right on the edge of that street? They are literally holding up or supporting the entire dividing line. They're the support vectors. You could actually get rid of all the other data points and that line wouldn't move an inch. The entire model is defined by just those few critical points. Pretty amazing. Okay, but let's be real. Real-world data is messy, right? It's almost never that clean and perfect. So what happens when some of the dots are on the wrong side of the line? What then? This is where the SVM has another clever move. A hard margin approach is a total perfectionist. It demands zero mistakes. But the problem with that is it can lead to something called overfitting, where the model learns the training data too perfectly, including all its little quirks, and then it totally fails when it sees new data from the real world. A soft margin is way more practical. It's okay with a few mistakes here and there, because that allows it to find a boundary that works better for the data as a whole. It trades a tiny bit of perfection for a whole lot more real-world usefulness. Okay, so what about an even tougher problem? What if your data's arranged in, say, a circle or some other weird shape where no straight line on Earth is ever going to separate it? This is where the SVM unleashes its superpower. It's called the kernel trick, and it is an incredible bit of mathematical gymnastics. Basically, the algorithm projects the data into a higher dimension, kind of like taking a flat 2D drawing and suddenly seeing it in 3D. And in that higher dimension, all of a sudden, a simple, flat plane can separate the groups perfectly. The different types of kernels you hear about are just different ways of making that dimensional leap, letting the SVM solve some ridiculously complex problems. Now, let's switch gears and look at a completely different way of thinking. So if the SVM is a geometer, this next algorithm is more like a detective. It doesn't draw lines in space. It solves problems by asking a series of really smart questions. Kind of like a game of 20 questions. A decision tree is pretty much exactly what it sounds like. It's a flowchart of questions. You start at the top at the first node, and it asks a simple question. Depending on your answer, you follow a branch down the tree until you land on a leaf, which is the final answer. And what's so great about this method is how transparent it is. You can actually trace the exact path of logic it took to get to a decision. So let's walk through a classic example to really see how this works. Our goal here is to decide if we should play a game based on the weather. So the algorithm looks at this data, and it might figure out that the most important question to ask first is, what's the outlook? If the answer is overcast, well, it looks like the answer is always yes, play. Easy. But if it's sunny, the answer's not so obvious. So the tree knows it needs to ask another question, like, okay, but what's the humidity? So how does it know which question to ask first? Well, its goal at every single step is to reduce something called impurity. You can think of it like this. You start with a big, messy box of different shapes, all mixed together. The algorithm looks for the one single question, like, is it a circle, that will split that messy collection into two less messy groups. The goal is to keep asking questions until you end up with boxes that only have one type of shape in them. It's always looking for the question that brings the most clarity. A single detective asking smart questions? That's great. But what if you could put together a whole committee of detectives and just have them all vote on the final answer? Well, that's the next logical step. See, a single decision tree can be really powerful, but sometimes it can get a little fixated on the weird quirks in the specific data it was trained on. So is one detective's opinion, no matter how logical, always enough to solve the case? And this is the absolutely brilliant idea behind what's called a random forest. Instead of trusting just one detective, you build a whole forest of them. You create hundreds of slightly different decision trees by showing each one just a random piece of the evidence. Then, to get your final answer, you just let them all vote. It's basically the wisdom of the crowd for algorithms. And this ensemble method is almost always way more accurate than any single tree could be on its own. So now we've met our two competing philosophies, the precise geometer and the logical detective. Let's put them side by side and figure out when you might want to hire one over the other. When you look at it this way, the choice gets a lot clearer. Our geometer, the SVM, is an absolute powerhouse when you have lots of dimensions, which makes it perfect for super complex jobs like image classification. Its strength is finding that one perfect boundary. But on the other hand, our detective, the decision tree, really shines when you need to understand why a decision was made. For things like financial risk or a medical diagnosis, you have to be able to explain your reasoning, and the tree's step-by-step logic is perfect for that. So here's the most important takeaway from all this. There's no magic bullet. There's no single best algorithm. One thinking style isn't just better than the other. The master geometer and the master detective, they each have their own unique strengths. And picking the right one is all about understanding the problem you're trying to solve. And that really leaves us with a much bigger question to chew on, doesn't it? As we hand over more and more critical decisions to these algorithms, in medicine, in finance, even in justice, which style of thinking do we actually prefer? The incredible power of the geometer, which is often a black box, or the clear, explainable reasoning of the detective? And maybe most importantly, who gets to make that call?